Tonight, we are going to confront a quiet crisis in modern science. For 30 years, cosmologists believed they had figured out the universe. The model worked, the predictions held. The math agreed with the measurements to 4 decimal places. Then a telescope a million miles from Earth started sending back data, and the data did not fit. By the end of this video, you are going to understand exactly why a generation of physicists is now openly rebuilding its assumptions. You are going to understand why one of the most successful scientific theories ever constructed may be quietly breaking apart. And you are going to understand what that means for everything we thought we knew about where we came from, what we are made of, and what the universe actually is. It begins with 6 galaxies in a photograph. They are real. Their distances have been confirmed multiple times by independent teams using different methods. Their light has been traveling for over 12 billion years to reach the camera that captured them. What is not confirmed, what no one yet knows, is how they exist. Under our current model of the universe, they cannot, and there are not 6 of them. There are dozens, possibly hundreds, with new candidates being added every observing cycle. The telescope that found them sits 1 million miles from Earth, in permanent darkness, behind a sunshield the size of a tennis court. Its golden mirror is 21 feet across, made of 18 hexagonal segments coated in a layer of gold so thin that the total amount of gold on the entire mirror weighs about as much as a golf ball. The telescope is called the James Webb Space Telescope, and in just over 3 years of operation, it has done something no scientific instrument in history has managed. It has found evidence that the story we tell about the universe, the careful, mathematically precise, beautifully confirmed story, may be incomplete, not at its edges, at its beginning. To understand what that means, we have to start with the model itself. Because the model is not some loose guess that scientists are precious about. The model is a triumph. It is one of the most successful scientific theories ever constructed by human minds. It predicted things that had not yet been measured, and then those things were measured, and the predictions held. It told us what the universe looked like when it was a few 100,000 years old, and then we built telescopes that confirmed it. It told us how galaxies should be distributed across billions of light years of space, and then we mapped them, and the maps agreed. It told us, with breathtaking precision, the temperature of the leftover heat from the Big Bang, and then we measured that temperature, and it matched to 4 decimal places. The model has a name, the Lambda Cold Dark Matter model. Cosmologists usually just call it lambda, CDM. The Greek letter lambda stands for the cosmological constant, the term Einstein added to his equations and then removed, the term that turned out to describe something real. Cold dark matter stands for the invisible substance that makes up most of the mass in the universe, the substance that does not interact with light but does interact with gravity, the substance whose gravitational fingerprints we have measured, but whose actual particles we have never caught. The model says that the universe began about 13.8 billion years ago, in a state of unimaginable density and temperature. It says that in the first tiny fraction of a second, the universe underwent a period of exponential expansion called inflation, during which space itself stretched faster than the speed of light. It says that after inflation, the universe was a hot, opaque soup of subatomic particles, and that this soup gradually cooled, formed atoms, became transparent to light, and then began the slow process of pulling itself together into the structures we now see. The key word in that timeline is slowly. The model says galaxy formation was a slow, grinding, generational process. Gas had to clump together under its own gravity. The first stars had to form, live their brief, violent lives, and explode. Those explosions had to seed the next generation of stars with heavier elements. Smaller galaxies had to collide and merge to form larger ones. Each step took hundreds of millions of years. Nothing could shortcut this process, because nothing moves faster than the speed of cause and effect. Even gravity propagates at the speed of light. 6 independent lines of evidence, measured by different teams, using different telescopes and different methods, all converged on this same picture. The cosmic microwave background, the leftover heat from the Big Bang, told us the age of the universe and the composition of matter and energy within it. The distances to distant supernovae told us the universe was accelerating in its expansion, which led to the discovery of dark energy. The large-scale distribution of galaxies, mapped across enormous volumes of space, told us how matter clumped over time. The abundance of light elements told us what the universe was made of in its first few minutes. The bending of light around massive objects told us where the invisible matter was hiding. The slight ripples in the cosmic microwave background told us about the structure of the very early universe. All 6 methods agreed. The agreement was so good, so detailed, so precise, that by the late 1990s, cosmologists used a phrase to describe the situation. They called it precision cosmology. The era of vague guesses was over. We had a model, and the model worked. Scientists did not just believe this model. They staked 30-year careers on it. They built telescopes designed to confirm specific predictions. They wrote textbooks that taught it as established fact. They built simulations that ran on supercomputers for months at a time, using lambda CDM as the foundation. And the simulations produced universes that looked, in broad strokes, like the universe we actually see. The model was not an idea anymore. It was the floor everyone was standing on. This is the situation James Webb arrived into. The telescope took 30 years to build. It cost about $10 billion. It had 344 single points of failure, each one capable of destroying the entire mission if it went wrong. The mirror had to unfold in space. The sun shield had to deploy through 5 separate layers. The secondary mirror had to swing out on its tripod. The entire spacecraft had to fly to a gravitationally stable point 1 million miles from Earth, called the second Lagrange point, where the gravity of Earth and the gravity of the Sun balance in a way that lets a spacecraft stay roughly stationary relative to both. If any one of those 344 steps had failed, the telescope would have been lost. There would have been no rescue mission. Unlike Hubble, which orbits close enough to Earth that astronauts can reach it, James Webb is too far away for any human intervention. Whatever it does alone. Every step worked. The telescope released its first images on July 12, 2022. The image that captured the world's attention was a deep field. A patch of sky no larger than a grain of sand, held at arm's length. In that tiny patch, the telescope found thousands of galaxies. Some of them were nearby. Most of them were ancient. Their light had been traveling for billions of years to reach the mirror. The astronomer who led the Deep Field project said something in the press conference that became famous in the field. She said she had opened a door expecting a small room and found a continent. She meant it as wonder. She meant it as the beauty of discovery. But within months, that same continent began producing results that made some of her colleagues stop sleeping. Because the galaxies were wrong, not all of them. The nearby galaxies looked the way they were supposed to look. The medium-distance galaxies looked the way they were supposed to look. But the most distant galaxies, the ones whose light had traveled the longest, the ones the telescope was specifically designed to see, those galaxies were not what anyone expected. They were too bright. They were too massive. They were too structured. They were too mature. And there were too many of them. To explain why this matters, we have to talk about something called look-back time. When you look at a distant galaxy, you are not seeing it as it is now. You are seeing it as it was when the light left it, which might have been 12 billion years ago. The further away a galaxy is, the further back in time you are looking. James Webb was designed to look further than any telescope before it. The point was not just to see far away. The point was to see early. The telescope's infrared sensitivity allowed it to capture light that had been stretched out by the expansion of the universe over billions of years. Light that no other instrument could detect. The expectation was clear. When James Webb looked at the early universe, it would see proto-galaxies, small, chaotic, gas-rich blobs, the building blocks, the raw material that would eventually, over the course of many billions of years, assemble into the mature galaxies we see in our cosmic neighborhood. That is not what the telescope found. It found galaxies that should not have existed yet. Galaxies with masses comparable to our own Milky Way, sitting in an era when the universe was less than 1 billion years old. Galaxies with billions of stars in them, in a time when our models said only a few 100 million stars should have formed across the entire visible universe. Galaxies with structure, real structure, disks, spirals, bars, organized rotation, the kind of structure that, according to every textbook ever written about galaxy formation, takes billions of years of mergers and gravitational settling to produce. The astronomers who first noticed this thought it was a measurement error. That is the correct response. When your data disagrees with 30 years of established physics, you check your data. They checked. The redshifts were correct. The galaxies really were as distant as they appeared. The light really had been traveling for the time the measurements indicated. Then they thought it was a fluke. Maybe just a few unusual galaxies, the cosmic equivalent of finding an outlier in a sample of millions. They looked at more data, more galaxies. The pattern held. The early universe was not full of proto-galaxies. It was full of mature ones. There is an analogy that gets used in the field, and it captures the strangeness of the finding better than any technical description. Imagine you walk into a construction site 3 weeks after the foundation was poured. You expect to see workers, scaffolding, partial walls, the beginnings of a building. Instead, you find a finished skyscraper. The doors are open, the lights are on, people are working in the offices. The plumbing is installed and functioning. And when you ask how this happened, the workers cannot tell you. They were as surprised as you are. This is roughly what James Webb is finding in the early universe. Not just one finished skyscraper, thousands of them, in every direction, at every distance. The pattern is not localized to one region of the sky. It is everywhere the telescope looks. The data is not in dispute. Multiple independent teams using different instruments on James Webb, analyzing the data with different software, have confirmed the basic observation. There really are massive, mature galaxies in the early universe. The question is not whether they exist. The question is how. There are a few proposed explanations, and each one has its own problems. Maybe star formation in the very early universe was more efficient than we thought, because the gas was denser and the conditions were more extreme. Maybe the first generation of stars was different from what we modeled, producing more mass per unit of gas. Maybe our simulations are missing some piece of physics that allowed galaxies to assemble more rapidly under conditions we have never directly observed. Maybe the dark matter halos that gave the gas something to fall into were larger or more numerous than we believed. Each of these explanations might be partially correct. None of them by itself fully explains the observations. And the deeper problem is that whatever explanation eventually emerges, it requires changes to a model that, until just a few years ago, seemed nearly complete. The astronomer who led the first major analysis of these impossible galaxies said something in an interview that became, in some sense, the defining quote of this entire situation. He said, "The detection is confirmed. The explanation is a mystery." That sentence is the doorway into everything that follows. Because the impossible galaxies are not the only thing James Webb has found that does not fit. They are the first thing, the most obvious thing, the thing that gets the headlines. But they are not by any measure the strangest result. Across multiple surveys, James Webb has now consistently found roughly 10 times more stellar mass in the early universe than our best simulations produce. 10 times. That is not a calibration error. That is not a statistical fluctuation. That is sustained pressure on the predictions we built using our model of how galaxies grow. The lead researcher on one of the most cited studies in the field, a woman named Karina Caputi, used a phrase in a 2024 paper that stuck with the field. She said her team's results on a galaxy called ZFUDS7329 had been giving her sleepless nights. The galaxy had a stellar mass comparable to a galaxy 10 times its age. There was no model that explained how it could exist. There was no calibration error that could account for it. The detection was real. The galaxy was real. The implications were not yet clear. This is where the first crack opens. Not as a single anomaly that might still be explained away, as a pattern. Something in our picture of the universe is wrong. The question is how wrong. We are about to spend the next 2 hours exploring the answer to that question. We are going to look at the galaxies that should not exist. We are going to look at the black holes that grew too fast. We are going to look at the numbers that disagree with themselves. We are going to look at the structures that are too big to have formed. We are going to look at the laws of physics that may not have always been the laws of physics. And by the end of this story, we will have arrived at a question much larger than James Webb itself. The question of what we are actually living inside. Pull back from the impossible galaxies for a moment. Take in the scale. We are not looking at a single anomaly. We are looking at the first crack in a foundation that everyone, including the people who built it, believed was solid. The crack is real. It is growing. And it is wider than the impossible galaxies alone can account for. In 2023, a team of astronomers at the University of Edinburgh announced the discovery of a galaxy that by every standard of cosmological orthodoxy should not have existed. They called it GS 9209. The galaxy was massive. It contained hundreds of billions of stars, comparable in stellar mass to the Milky Way. Its light had been traveling for over 12.5 billion years to reach Earth. We were seeing it as it had been when the universe was less than 2 billion years old. That alone would have been strange. But there was something stranger about GS 9209. It was dead. Galaxies, in the conventional understanding, do not simply stop forming stars. They cycle through gas, expel some of it, draw in more, merge with other galaxies, and continue the process for tens of billions of years. The Milky Way is still actively forming stars today, after about 13 billion years of operation. Quiescent galaxies, galaxies that have stopped forming new stars, are supposed to be a feature of the late universe, the result of long evolutionary processes that take many billions of years to complete. But GS 9209 had stopped. The team detected almost no new star formation. The galaxy had built its hundreds of billions of stars rapidly in the first 1 to 2 billion years after the Big Bang, and then it had simply shut down. The fire had gone out permanently. There is a useful analogy for this. Imagine you find a person who has lived a full life, 80 or 90 years, gone through every stage of human development, and then you discover that this person is 2 years old. Not figuratively, literally 2 years old. They are still in toddlerhood by every objective measure. But somehow, somewhere, they have already accumulated the experiences and the wear of a long life. That is the situation with GS 9209. The galaxy is structurally finished. Its history is over. But cosmically, it is barely a child. GS 9209 was not an isolated case. Within a year of its discovery, more dead galaxies appeared in James Webb's data. In 2024, the jwst E-Cells survey reported what its authors described as ultramassive quiescent galaxies at high redshift, galaxies that had grown enormous and then died before the universe was anywhere near old enough for either process to have happened according to the model. The headline of one of the papers used a deliberate phrase: too much, too young, too fast. Then came the galaxy at the center of the cosmological mass crisis. Its name was ZF-UDS 7329. The lead researcher on the study, an astronomer at Swinburne University, told reporters that this single galaxy had become one of the most cited pieces of evidence in what was now openly being called the cosmological crisis. The galaxy had a stellar mass equivalent to a galaxy 10 times its age. It had formed somewhere between 380 million and 700 million years after the Big Bang, an era so early that, according to the standard model, the dark matter halos, large enough to host such a galaxy, did not yet exist. The team checked the data the way any responsible scientist would. They considered measurement error. They considered contamination from foreground objects. They considered the possibility that the spectroscopy had picked up the wrong wavelengths. Every check came back the same way. The galaxy was real. Its mass was correct. Its distance was correct. The implication was simply that something fundamental was missing from our model of how the early universe assembled itself. The 10 times mass problem is now well established across multiple independent surveys. James Webb keeps finding roughly 10 times more stellar mass in the early universe than our simulations produce. That is not the kind of discrepancy that gets resolved with a calibration tweak. That is the kind of discrepancy that demands an explanation at the level of physics. Some astronomers have argued that revised analyses bring the discrepancy down, that better accounting for dust and luminosity could shrink the gap. Others argue the gap is real and irreducible. The debate is genuine. The data is being fought over in real time. A team at MIT proposed one possibility in 2024. They suggested that something called early dark energy, a form of dark energy that briefly turned on in the first few 100,000 years after the Big Bang and then faded away, could explain both the impossible galaxies and the Hubble tension at the same time. The proposal is elegant. It also requires the existence of a phenomenon for which we have, at present, no direct evidence. Other researchers have proposed that the first generation of stars was different from what our models assume, that they were more massive, more energetic, more efficient at converting gas into stellar mass, that the conditions in the early universe allowed for what they called feedback-free star formation, a runaway process in which gas collapsed and ignited so rapidly that it did not have time to be blown away by the radiation pressure of the new stars. Still others have suggested that our entire framework for thinking about dark matter in the early universe needs revision. That the halos that supposedly seeded the first galaxies were not the slow, gradual accumulations we modeled, but something far more dramatic: direct collapse, primordial fluctuations. Or maybe dark matter itself does not behave the way we have been assuming. Each of these proposals is being actively debated. Each of them has its supporters and its critics. None of them has emerged as the consensus answer. What everyone agrees on is that something has to give. The model that predicted small, slow, gradual galaxy formation in the early universe is not what James Webb is showing us. But the cracks do not stop with dead galaxies and impossible masses. Because James Webb has also found something else. Something that, in many ways, is even harder to explain. It has found spiral galaxies in the early universe. And spirals are not supposed to be there. To understand why this matters, you have to understand what a spiral galaxy actually is. The Milky Way is a spiral. Our solar system sits in one of its arms, about 2/3 of the way out from the center. From far above, the galaxy would look like a slowly rotating pinwheel, with 2 main arms and several minor ones curling out from a central bulge. The structure looks elegant in a photograph, but it is not simple to produce. A spiral galaxy is a kind of equilibrium. It is the result of billions of years of gravitational settling, of mergers and accretions, of gas being pulled inward and stars being thrown outward, of the slow stabilization of a rotating disk. The arms themselves are density waves, patterns of slightly higher star formation that move through the disk like ripples through a pond. To produce a clean, 2-armed spiral structure, you need a stable disk. To produce a stable disk, you need time, a lot of time, billions of years. For most of the history of astronomy, this was considered settled. The earliest galaxies, the model said, were chaotic, clumpy, asymmetric. They were collisions in progress, mergers in motion, gas-rich blobs in the process of figuring out what they wanted to be. Spirals were supposed to emerge later, after the dust had settled. In late 2024 and early 2025, this picture began to fall apart. A team using James Webb identified a galaxy they nicknamed the Big Wheel. It was massive. It was structurally mature. It had a clear spiral pattern with multiple arms, and it existed in the first 2 billion years of the universe. The researcher who led the discovery, an astronomer at Swinburne University, said in an interview that for a galaxy this massive in this early universe, you would expect it to be elliptical, smooth, featureless. You would not expect a spiral. The fact that you got one means that whatever formed it either happened in a remarkably neat way, allowing the galaxy to keep spinning without violent mergers, or most of its mass formed in place rather than being assembled from collisions. Both explanations are uncomfortable. Both require the early universe to have behaved differently from our model. And the Big Wheel was not alone. Multiple confirmed early spirals have now been catalogued. The University of Manchester announced one such structure in 2023, a clean 2-armed spiral whose light had traveled over 11 billion years to reach Earth. The structure was unambiguous. The arms were visible. The disk was rotating. The galaxy was, in every sense, a finished product. There is another analogy that gets used in the field for this kind of discovery. If a flowing river requires geological time to carve a stable canyon, what would it mean to find a canyon already fully carved in the week after snowmelt began? You would not necessarily conclude that the river had been there longer than you thought. You might conclude that something else carved the canyon, something faster, something more powerful, something not in your current understanding of how rivers work. The early spirals are saying something similar. The universe was settling down, organizing itself, producing mature gravitational structures billions of years before our model said it was possible. And these are not rare outliers. They appear frequently enough in different surveys and at different distances to suggest that the process was common. Whatever it was, we just do not know what it was. In October of 2025, a team at the University of Cambridge published a different kind of finding. They had analyzed more than 250 young galaxies, observed when the universe was between 800 million and 1.5 billion years old. The point of the study was to look at the gas motions within these galaxies, to see whether they had begun to settle into smooth, rotating disks or were still chaotic, clumpy, and turbulent. The finding was nuanced. Most of these galaxies were still chaotic. They had not yet settled into disks, but mixed in among them were galaxies that had already organized themselves. The dawn of disks, the paper called it. The transition from chaos to order was happening earlier and faster than the model predicted. Some galaxies were still in the process of organizing themselves. Others had already finished. The universe was a strange mix of expected and unexpected, of confirmed predictions and broken ones. Now let us add one more layer. Because alongside the impossible galaxies and the early spirals, James Webb has found something else, something darker. It has found supermassive black holes. Black holes are gravitational sinks, so dense that not even light can escape them. The smallest ones are formed by the collapse of dying massive stars, and they have masses a few times what our home star has. The largest ones, the supermassive black holes that sit at the centers of large galaxies, are billions of times more massive. The supermassive black hole at the center of the Milky Way, called Sagittarius A star, has a mass about 4 million times our home star's mass. The largest known supermassive black holes are tens of billions of solar masses. How these objects form is one of the deepest unsolved problems in astrophysics. The standard model says that supermassive black holes grow over time, starting from smaller black holes that gradually accumulate matter. The rate at which any black hole can grow by accretion is limited by something called the Eddington limit. The Eddington limit is a balance between the gravitational pull of the black hole, which pulls matter inward, and the radiation pressure produced by the matter as it falls in, which pushes matter outward. If a black hole tries to grow too fast, the radiation pressure overwhelms the gravitational pull, and the gas gets pushed away. There is an analogy for this that astronomers like to use. Imagine you have a swimming pool and you want to fill it as fast as possible with a garden hose. There is a maximum rate at which water can flow through the hose. You cannot exceed that rate, no matter how desperately you want the pool to fill. The Eddington limit is the garden hose for black hole growth. There is a maximum rate. You cannot exceed it. According to the standard picture then, black holes need time to grow large. Lots of time. Billions of years. A supermassive black hole with 1 billion solar masses must have started smaller and grown over geological timescales. The math of the Eddington limit makes this almost a logical necessity. James Webb has now confirmed the existence of supermassive black holes with hundreds of millions to billions of solar masses at extremely early times in the universe. 400 million years after the Big Bang. 500 million years after the Big Bang. Times so early that the Eddington limit cannot account for them. There simply was not enough time for these black holes to grow to their observed masses, even if they had been accreting matter at the maximum rate continuously since the moment of their formation. The most distant black hole ever confirmed was announced in August of 2025. It is called Kuiper's LRDZ9, and it sits at a redshift of 9.288, which corresponds to about 500 million years after the Big Bang. Its mass is around 300 million times the mass of our home star. There is no model of conventional black hole growth that can produce this object in the time available. Something else must be going on. One possibility is direct collapse. In this scenario, very dense clouds of gas in the early universe collapse directly into massive black hole seeds, skipping the star formation stage entirely. Instead of starting from a tiny stellar mass black hole and growing for billions of years, the seed black hole would have started with a mass of tens of thousands to hundreds of thousands of solar masses ready-made. From that head start, it could plausibly have grown to the observed masses within the time available. Direct collapse used to be considered exotic, a possibility, but not the leading explanation. James Webb has changed that calculus. The discovery of so many massive black holes so early in the universe has made direct collapse one of the leading candidates for how supermassive black holes actually form. And in February of 2026, a team led by Fabio Paccucci at Harvard published evidence that one of the strangest categories of objects James Webb has discovered may, in fact, be these direct collapse black holes in action. They are called the little red dots. The name is unromantic, but it captures the appearance. In James Webb's images, certain compact red objects appear scattered across the sky, point-like in their morphology, dominated by red light. They were first noticed in late 2022 and early 2023, and for a while no one knew what they were. They were too bright to be normal galaxies of their age. They were too compact to be galaxies at all in many cases. They appeared in numbers far exceeding what any model predicted. For 2 years, theorists proposed competing explanations. Maybe they were compact star-forming galaxies. Maybe they were dust-obscured quasars. Maybe they were something genuinely new. The debate consumed conferences. By 2025, the evidence was tilting toward the conclusion that the little red dots are accreting black holes hidden inside dense clouds of gas that obscure their light and shift it to the red end of the spectrum. The Paccucci paper went further. It argued, based on radiation hydrodynamic simulations, that the specific properties of the little red dots are best explained if they are direct collapse black holes, actively accreting from their environment. If the interpretation holds up, the little red dots are the smoking gun for direct collapse black hole formation. They would be evidence that the early universe was producing massive black hole seeds in large numbers through processes that the conventional model does not include, and every one of them is connected back to the larger crisis. The early universe was running engines we did not know it had. GS 9209, the dead galaxy we started this section with, may itself have been killed by one of these engines. The favored explanation for why it stopped forming stars so abruptly is that the supermassive black hole at its center entered an active phase, blowing the galaxy's gas reservoir away with the force of its radiation. The same kind of process that, in larger galaxies, can shut down star formation across an entire system. In a young galaxy, with less gas to work with, the effect would have been faster and more complete. The black hole turned the lights out. We are now seeing a pattern that the model did not predict. Galaxies forming faster, black holes growing faster, disks settling faster, stars dying faster. The early universe was not the slow, gradual process the textbooks described. Whatever it was working at a tempo our equations do not match, and we built our cosmology around the assumption that the tempo would be different. There is one more piece of the early universe puzzle we have to address before moving on. The first generation of stars themselves. In the standard picture, The universe entered a period called the Cosmic Dark Ages after the Big Bang. The early universe was so hot and so opaque that no light could escape it. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, and the radiation that had been bouncing between charged particles could finally travel freely. That radiation became what we now call the cosmic microwave background. After that moment, the universe was transparent, but it was also dark. There were no stars yet. There were only clouds of hydrogen and helium gradually clumping together under gravity. For a few 100 million years, the universe contained essentially no visible light. The Dark Ages. Then the first stars began to form. They are called population 3 stars. By an accident of historical naming, the label comes from a system invented in the 1940s to classify stars by their metal content, with population 1 being modern stars rich in heavy elements, population 2 being older, metal-poor stars, and population 3 being a theoretical category for stars made of nothing but the primordial hydrogen and helium produced in the Big Bang. For decades, population 3 stars were a theoretical prediction. They had to exist. The math demanded it, but no one had ever observed one. They were too far away, too brief, too rare in the surviving record. Their existence was inferred from the fact that the second generation of stars, the ones we can observe, contains elements that could only have been produced by their stellar ancestors. Every atom of carbon in your body, every atom of oxygen, every atom of iron, traces its ancestry to a star that died before our galaxy was born. The population 3 stars themselves were supposed to be different from anything alive today. The conditions in the early universe, with no heavy elements to help cool collapsing gas, allowed for the formation of stars far more massive than anything that forms now. Hundreds of solar masses, possibly even thousands. They would have been bluish-white, brief, catastrophically energetic. They would have burned through their fuel in just a few million years, and then most of them would have ended their lives in spectacular supernovae or as direct collapse black holes. James Webb was supposed to find them. That was one of the explicit goals of the mission. For 3 years, the telescope hunted, and for 3 years, the search came up empty or contested. Candidates were proposed and then ruled out. The faint, brief signatures of population 3 stars were so subtle that they bordered on the limits of what the telescope could detect. Then, in late 2025, the picture began to change. A team led by Ari Vispel at the University of Toledo published a detailed analysis of a small distant galaxy called LAP-1b. The galaxy is gravitationally lensed, meaning its light has been magnified by the gravity of an intervening galaxy cluster, which allowed James Webb to see it more clearly than it otherwise could. The analysis suggested that LAP-1b contained population 3 stars. The galaxy's emission lines showed signatures consistent with hydrogen and helium, but lacked the lines you would expect from heavier elements. The match to theoretical predictions for population 3 stellar populations was strong. In April of 2026, a separate team led by Roberto Maialino at Cambridge published companion studies identifying what may be the most compelling evidence yet for population 3 stars in a small object near the galaxy GNZ11. By May of 2026, the LAP-1b results had been published in Nature, describing what had become the most chemically primitive star-forming galaxy ever observed, with an oxygen content just 1/240th of the Sun's. These are not yet definitive detections. Caution remains warranted. The signals are at the edge of what James Webb can resolve, and independent confirmation is still being sought. But the trajectory of the evidence has shifted. After 3 years of frustrated searches, we may now be seeing the chemical fingerprints of the first generation of stars in the universe. And here is the strangeness embedded in those fingerprints. Even before any of this, James Webb had been finding heavy elements in early galaxies at levels that should not be possible. The chemical enrichment of the universe, the gradual build-up of heavier elements through successive generations of stars, was supposed to be slow. The first stars had to live, die, and seed the next generation. The next generation had to live, die, and seed the one after that. Each cycle takes hundreds of millions of years. And yet James Webb has detected oxygen, carbon, nitrogen, and other heavy elements in galaxies whose light reaches us from the first half-billion years of cosmic history. The reionization budget tells us something similar. Reionization is the process by which the hydrogen in the early universe was stripped of its electrons by ultraviolet radiation, transitioning the universe from a neutral, opaque state to the ionized, transparent state we observe today. The reionization budget refers to the amount of ultraviolet radiation produced by early galaxies, the radiation that drove this transition. The standard model predicted a certain amount of UV from early galaxies. James Webb has consistently found 3 to 5 times more than expected. The early galaxies were brighter, more energetic, and more productive than the model allowed. Whatever the first stars were, they were more extreme than we modeled, more massive, more energetic, more efficient. Something about the conditions right after the Big Bang was wilder than our equations allowed. Pull back from all of it. Galaxies assembling on accelerated timescales, chemistry showing up early, black holes reaching enormous mass within an impossibly small window, disks settling into rotation before they should have organized. The first stars producing more ultraviolet light than our predictions allowed. The mass budget of the early universe coming in at roughly 10 times what the model produced. It is not just one anomaly. It is a pattern. The entire early universe was operating in a way the model cannot account for, and we are not done. The strangeness we have looked at so far has been about the structures themselves, what they are, where they are, when they appeared. The next layer is about the numbers, the measurements that should agree with each other and do not, the constants that should be constant and may not be, the geometry that should be smooth and is not. The fractures get deeper from here. The universe has an expansion rate. It is a single number. It tells you how fast galaxies are receding from each other, on average, per unit of distance. The number is called the Hubble constant, after Edwin Hubble, the astronomer who first established in 1929 that the universe was expanding. The Hubble constant should, in principle, be one number. There is one universe. It is expanding at one rate. The number might be hard to measure precisely, but it should not depend on how you measure it. If you use one method, you should get the same answer as if you used another method. Different routes to the same destination should arrive at the same place. For most of the 20th century, this was not a problem because the measurements were imprecise. Astronomers disagreed about the Hubble constant. Some said it was around 50 kilometers per second per megaparsec. Others said it was closer to 100. The error bars were large enough that everyone's measurements overlapped within their uncertainties. Disagreement was expected. The methods were too crude for the disagreement to mean anything beyond ordinary measurement difficulty. Then the methods got better, and the disagreement did not go away. There are two main ways to measure the Hubble constant. The first method, the local method, uses what astronomers call the distance ladder. You start with objects whose distances you can measure directly. Stars close enough to show parallax, the tiny shifts in their apparent position as Earth moves along its orbit each year. You use those to calibrate the distances to slightly more distant objects, like a class of pulsating stars called Cepheid variables, whose intrinsic brightness can be inferred from how fast they pulse. You use the Cepheids to calibrate the distances to galaxies that contain them. And you use those galaxies to calibrate the distances to a class of supernovae called Type 1, a supernovae which have a very specific predictable brightness and can be seen across enormous distances. Each rung of this ladder is a step further into the cosmos. By the end, you can measure the distance to galaxies hundreds of millions of light years away. And once you know the distance, and you measure how fast the galaxy is moving away from you using its redshift, you can compute the Hubble constant. The local method gives you a number. The second method, the early universe method, uses the cosmic microwave background. The CMB is the leftover heat from the Big Bang, the light that escaped when the universe became transparent about 380,000 years after its beginning. The CMB has tiny temperature variations across the sky, ripples imprinted on it by the conditions of the early universe. By analyzing the precise pattern of these ripples and feeding the analysis into the lambda CDM model, cosmologists can compute what the Hubble constant must be in order to evolve the early universe into the universe we observe today. The early universe method gives you a number. The two numbers disagree. The local method, in its most precise iterations, gives a value around 73 kilometers per second per megaparsec. The early universe method gives a value around 67. The gap is about 9%. In everyday life, 9% is nothing. In fundamental physics, 9% is a crisis. For a long time, cosmologists assumed the gap would close. Both methods had sources of uncertainty. As measurements improved, the numbers would converge. That was the expectation. It was reasonable. It made sense. It just turned out to be wrong. When James Webb came online, one of its first major projects was to use its superior infrared sensitivity to remeasure the distances in the local distance ladder, looking for hidden systematic errors that might have biased the previous results. The Hubble Space Telescope had been the workhorse of these measurements for years, and one of the leading critiques of the local method was that crowded star fields could introduce errors when Hubble tried to resolve individual Cepheid variables. With James Webb's superior resolution, these errors should be eliminated. The results came back in 2023 and 2024. The lead author of one of the most cited papers, Adam Rees at Johns Hopkins, said the team had now spanned the whole range of what Hubble had previously observed, and they could rule out measurement error as the cause of the Hubble tension with very high confidence. James Webb's measurements agreed with Hubble's. The local value did not budge. It stayed around 73. Other teams used different approaches. A team led by Jensen used a method based on surface brightness fluctuations in elderly elliptical galaxies, a technique that did not rely on Cepheids or Type 1, a supernovae, at all. Their value came in at 73.8. A team led by Wendy Friedman had previously argued that an alternative method based on the tip of the red giant branch gave a lower value, closer to the CMB number. Independent teams have not been able to reproduce that finding. In April of 2026, an international collaboration led by the Head Zero Distance Network published what is currently the most precise local measurement to date. They got 73.5 to 0, plus or minus 0.8 to 1. The uncertainty has been reduced to less than 1%. The gap between local and early universe measurements has now been confirmed at over 5 sigma significance, the gold standard for a scientific discovery. The chance that this disagreement is due to random error has been reduced to essentially zero. The Hubble tension is not a tension anymore. It is a fact. The universe, according to two rigorous and well-tested methods, is expanding at two different speeds simultaneously. That sentence sounds absurd. That is where the data points. James Webb did not solve the Hubble tension. James Webb deepened it. By removing the most plausible source of error, the telescope removed the most plausible escape route. The two values are real. They disagree, and our model of cosmology cannot accommodate both of them. But that is not the only number that has gone sideways. There is a second, less famous tension that has been building alongside the Hubble one. It is called the SATE tension. SATE is a parameter that describes how clumpy the matter in the universe is. It is a measure of the amplitude of density fluctuations on a particular scale, related to how matter has gathered itself into galaxies and clusters under the influence of gravity over the history of the universe. The early universe measurements of SATE, derived from the cosmic microwave background, predict a certain amount of clumpiness in the present-day universe. The late universe measurements, derived from observations of how galaxies are actually distributed and how their light is gravitationally lensed by foreground matter, give a different number. The late universe is less clumpy than the early universe predicts it should be. The tension is smaller than the Hubble tension, perhaps 2 to 3 sigma significance rather than 5. But it is real, and it has been consistent across multiple independent surveys. Here is the structural problem. If the Hubble tension were the only anomaly, you could imagine that some single modification of the model might fix it. Maybe dark energy behaves slightly differently than we thought. Maybe there is a new particle that briefly contributed to the energy density of the early universe. Some plausible patches have been proposed. But the SATE tension is independent. It points in a slightly different direction. The same patches that fix the Hubble tension do not always fix the SATE tension. Sometimes they make it worse. The two anomalies are not telling us the same story. They are telling us that whatever is wrong with the model is wrong in more than one place. It is not one anomaly. It is two anomalies, pointing in different directions against the same model. Now we have to step further, because beyond the broken numbers, there is the broken substance. We have to talk about dark energy. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. The universe was supposed to be slowing down, gravity pulling everything back toward everything else. Instead, in the late 1990s, two teams independently measured the distances to very distant Type 1, a supernovae, and discovered that the universe is not slowing. It is speeding up. The expansion is accelerating. Something is pushing the universe outward. We call that something dark energy. The discovery won the Nobel Prize in 2011. It was one of the great surprises of modern science. And the explanation we have for it, in the Standard Model, is the cosmological constant. The same lambda that Einstein once added to his equations and then removed, the same term that lambda CDM is named after. The cosmological constant is supposed to be a fixed property of space itself, a kind of intrinsic energy density that pushes everything apart at a constant rate. The trouble is that when you try to calculate the value of the cosmological constant from first principles using quantum field theory, the predicted value is wrong. Not slightly wrong, spectacularly wrong. The theoretical prediction is somewhere between 50 and 120 orders of magnitude larger than the observed value. Depending on how you count, the discrepancy is between 10 to the 50 and 10 to the 120. a 1 followed by 120 zeros. That is the gap between theory and observation. Physicists have called this the worst theoretical prediction in the history of physics. They have called it the largest discrepancy between theory and experiment in all of science. They have called it the vacuum catastrophe. None of those names is an exaggeration. If the cosmological constant were as large as theory predicts, the universe would have expanded so rapidly after the Big Bang that no atoms could have ever formed, no structures could ever have assembled, no galaxies, no stars, no planets, no us. The fact that we exist, the fact that the universe contains coherent matter at all, requires the cosmological constant to be vastly, mysteriously smaller than our most fundamental theories say it should be. We have lived with this discrepancy for decades. It is one of the deepest unsolved problems in physics, and for most of that time, the cosmological constant has been treated as a placeholder. We use it because it works. The model agrees with observations if you plug in the observed value, but there is no derivation of that value from first principles. There is no explanation for why it has the value it has rather than some other value. The number is just there, inserted by hand, a free parameter. This is the situation that the dark energy spectroscopic instrument inherited. DESI, the four-letter acronym used to refer to it, is a galaxy survey project. It sits on top of a telescope at Kitt Peak in Arizona, and it has been mapping the positions of millions of galaxies and quasars across billions of years of cosmic history. The point of the survey is to measure how dark energy has affected the expansion of the universe over time. By looking at the distribution of galaxies at different distances, DESI can reconstruct the expansion history. And the expansion history, in principle, tells you whether dark energy is a fixed cosmological constant or whether it is something that changes over time. In April of 2024, DESI published its first year of results. The findings were, to put it carefully, unexpected. The data hinted, at a statistical significance of about 2 to 3 sigma, that dark energy might not be a constant after all. It might be evolving. Its strength might be changing over time. The cosmological constant might not be a constant. In March of 2025, DESI released its 3-year results. The signal had strengthened. Different combinations of DESI data with other cosmological measurements gave significance levels ranging from 2.8 sigma to 4.2 sigma. The lead researcher on the analysis said that at 4.2 sigma, the team was getting to the point of no return. The evidence was coming from multiple independent datasets. It was not a fluke. It was not noise. It was beginning to look like a discovery. By April of 2026, DESI had completed its full-planned survey of the sky, mapping more than 50 million galaxies. The dark energy story was not going away. It was getting stronger. The data still does not reach the gold standard of 5 sigma, but it is closing in. If dark energy is not constant, the implications are vast. The cosmological constant has been the foundation of our model of how the universe will end. If lambda is fixed, the expansion accelerates forever. The galaxies recede into ever greater isolation, and the universe gradually fades into a cold, dark, dilute state called heat death. That is the standard prediction. The big freeze. If dark energy is evolving, none of that is guaranteed. Depending on how it evolves, the universe could end in many different ways. It could enter a phase of decelerating expansion. It could recollapse in a big crunch. If the dark energy becomes more negative over time, the expansion could accelerate so violently that it tears apart galaxies, stars, planets, and eventually atoms themselves, in an end called the Big Rip. The fate of everything we can observe depends on which kind of dark energy is actually out there. And the answer, for the first time in decades, is genuinely unclear. The framework that physicists use to think about evolving dark energy is called quintessence. The name comes from the ancient Greek idea of a fifth element beyond earth, water, air, and fire. In modern cosmology, quintessence refers to a scalar field that fills space and behaves like dark energy, but whose strength can change over cosmic time. There are various models of how quintessence could work. Some predict subtle deviations from the cosmological constant. Others predict more dramatic shifts. DESI's data is, broadly, consistent with some kinds of quintessence and inconsistent with the simple cosmological constant. If dark energy is not constant, if it is not a fixed property of space but a field that changes, then our model of the universe's past and future needs to be rewritten simultaneously. The story of how everything began and the story of how everything ends are both wrong. Or at least, both have to be updated. The neat story of the Big Bang, the long middle, and the ultimate heat death depended on a stable cosmological constant. Without it, every chapter of cosmology becomes provisional. There is one more piece of the puzzle to fit into this section. We have talked about the broken numbers, the Hubble tension, and the Sate tension. We have talked about the broken substance, dark energy. We have not yet talked about the broken scaffolding, the invisible architecture that holds the visible universe together, dark matter. Dark matter is the term for the gravitational mass that we know exists, because we can measure its gravitational effects, but that we have never directly detected. It does not emit light. It does not absorb light. It does not interact with the electromagnetic force in any detectable way. But it has gravity, and its gravity is what holds galaxies together. Without dark matter, the stars in the outer regions of galaxies would not have enough gravitational pull to keep them in orbit, and they would fly off into intergalactic space. With dark matter, the math works. The standard picture of dark matter is that it consists of some kind of cold particles. Particles that move slowly compared to the speed of light, particles that interact only through gravity and possibly the weak nuclear force. These particles have been hunted in laboratory experiments for over 30 years, using deep underground detectors built to shield them from cosmic ray contamination. The experiments have produced null results. The detectors have not detected. Whatever dark matter is, it has eluded direct laboratory observation. In the absence of laboratory confirmation, our understanding of dark matter comes entirely from its gravitational effects. We have built models of how dark matter should be distributed in the universe, based on the assumption that it is cold, collisionless, and weakly interacting. The models predict that dark matter formed halos around galaxies and galaxy clusters, providing the gravitational scaffolding on which visible matter assembled itself. James Webb's observations are now placing pressure on this picture. The impossible galaxies, the early black holes, the rapid structure formation, all of these require more dark matter, or different dark matter, or differently distributed dark matter than our standard models predicted. There are three uncomfortable possibilities. The first possibility is that our simulations need adjustment. Maybe we have been modeling the formation of dark matter halos with too little resolution, or with the wrong assumptions about how gas interacts with dark matter, or with some other tractable error. This is the most conservative explanation. It does not require new physics. It just requires that we have made calculation mistakes. The second possibility is that dark matter in the early universe behaved differently from dark matter today. Maybe it was warmer. Maybe it interacted with itself in ways we have not accounted for. Maybe its distribution was lumpier than our models predict. This is more uncomfortable. It implies that dark matter has properties we have not yet identified, properties that would have to manifest in laboratory experiments if we knew what to look for. The third possibility is the deepest. It is the possibility that dark matter is not what we think it is, that our entire framework for understanding the invisible mass of the universe is wrong. The third option would not require adjusting a model. It would require rebuilding one. There is an alternative theory that has been quietly waiting in the wings for 40 years. It is called MOND, Modified Newtonian Dynamics. The idea was proposed by the Israeli physicist Mordechai Milgrom in 1983. The proposal was simple. What if there is no dark matter, and instead the laws of gravity work slightly differently at very low accelerations than they do at the higher accelerations we see in the solar system? MOND has been controversial since its inception. It has had successes, particularly in explaining the rotation curves of individual galaxies without invoking dark matter. It has had failures, particularly in explaining the dynamics of large galaxy clusters and the cosmic microwave background. For decades, the mainstream consensus has been that MOND is wrong and dark matter is real. But the consensus has never been unanimous. And as the cracks in the standard model widen, MOND and its descendants have been receiving renewed attention. The fact that they cannot easily explain the CMB no longer feels as decisive when the CMB-derived parameters are themselves in tension with everything else. Pull all the way back. The numbers disagree. The substance is changing. The scaffolding is uncertain. And beneath all of them, 95% of everything is invisible. The model that held those 95% in place is cracking under the weight of the 5% it was supposed to explain. We started this section with one number, the Hubble constant, that should be unique and is not. We have arrived at a place where almost every fundamental parameter of cosmology is under some kind of pressure. The expansion rate, the clumpiness of matter, the behavior of dark energy, the nature of dark matter. You can perhaps see now why some cosmologists describe this moment as a crisis, not a hyperbolic crisis, a real one. The model is not collapsing all at once in a single dramatic refutation. It is being chipped at from multiple directions simultaneously by independent observations using different instruments, all pointing toward the same conclusion. Something is wrong. We do not yet know what. We do not yet know how wrong. And we are still not at the deepest layer. The strangeness we have looked at so far has been about the contents of the universe. The next layer is about the assumptions underneath the contents, the assumptions that allow us to write the equations at all. To do cosmology, you have to make an assumption. You have to assume that the universe is, on the largest scales, the same everywhere. The same in every direction, the same at every location, with the same laws of physics operating consistently throughout. This assumption is called the cosmological principle, and it is not optional. Without it, the equations that govern the evolution of the universe become unsolvable. Einstein's field equations, the foundation of modern cosmology, are nonlinear differential equations of formidable complexity. To solve them for the universe as a whole, you have to simplify. You have to assume symmetry. You have to assume that what is happening over here is also happening over there, and what is happening today is, on average, the same kind of thing that was happening yesterday. The cosmological principle is the mathematical permission slip that lets cosmologists write equations at all. The principle has held up well for most of the history of modern cosmology. When we look at the universe on large scales, when we average over enough volume, the distribution of matter does appear to be roughly uniform. The cosmic microwave background is almost perfectly the same temperature in every direction, varying by only 1 part in 100,000. The large-scale distribution of galaxies, when smoothed over hundreds of millions of light-years, looks similar in every direction we point our telescopes. The principle defines a maximum size for structures in the universe. Gravity, the force that builds galaxies and clusters and superclusters and filaments, takes time to assemble matter into coherent structures. Given the age of the universe and the speed at which gravitational influence can propagate, theory tells us that there is a ceiling on how large any single structure can be. The number cosmologists use is approximately 1.2 billion light-years. Anything significantly larger than that should not exist. There has not been enough time since the Big Bang for gravity to have built it. This is the prediction. The observed universe should agree. It does not. The first violation was the Sloan Great Wall, identified in 2003. The structure was so large that it was initially dismissed as a likely artifact of the survey method. Then, more measurements came in. The wall was real. It was about 1.4 billion light-years across, slightly over the theoretical limit, but close enough that some cosmologists held out hope that better statistics would eventually reduce its apparent size. That hope did not survive what came next. In 2013, an international team announced the discovery of the Hercules Corona Borealis Great Wall. The structure was a vast concentration of galaxies, observable through the gamma-ray bursts that occur within them, spanning roughly 10 billion light-years. 10 billion. The theoretical limit was 1.2. The wall exceeded the limit by a factor of about 8. To put that scale in human terms, 10 billion light-years is more than 70% of the age of the visible universe. It is a structure so large that even if you could travel at the speed of light, it would take you 10 billion years to cross it from end to end. The cosmological principle says nothing this large should exist within the time available since the Big Bang. And yet there it is, mapped, statistically significant, confirmed. The wall was dismissed by some cosmologists as a possible statistical fluke. The argument was that the gamma-ray burst sample was small enough and the method sensitive enough to alignment artifacts that the structure might not be as real as it appeared. But further analysis has not made the structure go away. It has remained in the catalogue, and it has been joined by others. In 2021, a graduate student named Alexia Lopez at the University of Central Lancashire announced the discovery of what she called the giant arc. The structure spanned about 3.3 billion light-years across the sky, identified through the absorption signatures of ionized magnesium atoms in the spectra of background quasars. The arc was located about 9.2 billion light-years from Earth. Like the Hercules Corona Borealis Great Wall, it was far too large to fit within the theoretical limits of structure formation. In 2024, Lopez announced a second ultra-large structure in the same region of the sky, at the same distance from Earth. She called it the Big Ring. It was approximately 1.3 billion light-years in diameter, with a circumference of about 4 billion light-years. From Earth, the ring would appear to span an area of the sky that the diameter of about 15 full moons could cover. It was, as Lopez described it, a nearly perfect ring shape, though more detailed analysis suggested it might actually be a corkscrew or coil-viewed face-on. The two structures, the arc and the ring, were not only enormous individually, they were only 12 degrees apart in the sky. They sat at the same cosmic distance, meaning their light had traveled the same length of time to reach us, meaning they existed at the same cosmic epoch. Lopez and her colleagues raised the possibility that together they might form an even larger cosmological system, a system whose size and geometry have no precedent in the standard model. This is where the picture has gotten complicated, because the standard model has not been silent in response. In February of 2025, a team led by Til Sawala at the University of Helsinki published computer simulations showing that structures of ring-like geometry and similar size to the Big Ring can, in fact, form within the framework of lambda cold dark matter, given enough volume to sample. The simulations did not eliminate the strangeness of finding such a structure exactly where we found it, but they pushed back against the strongest interpretations, suggesting that the Big Ring might be a rare statistical occurrence rather than a definitive violation of the cosmological principle. The Hercules Corona Borealis Great Wall has received less of this kind of vindicating analysis. Its size remains too far above the theoretical limit to be easily explained by statistical chance. Some researchers have proposed that the wall might be a chance alignment of unrelated structures that only appears connected because of the way the data was binned. Others have argued that the structure is real and the limit is wrong. The current state of the debate is genuine uncertainty. The cosmological principle is not yet broken, but it is under pressure. The structures we have found are challenging the foundational assumption that allows cosmologists to write equations at all. If the principle is mostly correct, with rare exceptions, the framework survives. If the principle is significantly wrong, the framework needs serious revision. We do not yet know which it is. There is one more piece of evidence that pushes in the same direction, and it is more subtle than the giant structures. It is something the universe seems to have left in its oldest light, the cosmic microwave background, and it should not be there. The CMB, again, is the leftover heat from the Big Bang. It is the most ancient light in existence, dating from the moment when the universe became transparent. Across the sky, the temperature of the CMB is almost uniform, varying only by tiny amounts. Those tiny variations are themselves rich with information about the conditions of the early universe. When cosmologists analyze the patterns in the CMB, they decompose them into mathematical modes, looking at how temperature varies on different angular scales. The lowest modes describe the largest patterns. A perfectly random universe, born in an explosion with no preferred direction, should show no preferred orientation in its CMB modes. Statistically, the patterns at different scales should be independent of each other, oriented randomly with respect to each other and to any external reference direction. That is not what cosmologists found when they looked carefully at the CMB. Multiple analyses, beginning in the early 2000s and continuing through the WMAP and Planck satellite missions, identified an alignment between the lowest modes of the CMB and certain directions in space. The structure has been called the axis of evil, a half-joking name coined by the physicist Joao Magejo that has stuck. What the alignment means is genuinely unclear. The CMB's lowest modes appear to align with the ecliptic plane, the plane of Earth's annual orbit. They appear to be correlated with the direction of motion of our local group of galaxies relative to the CMB itself. The alignments are small. The statistical significance is debated. Some researchers attribute the patterns to foreground contamination, the inevitable leakage of more nearby radiation into the CMB measurements. Others argue that the alignments are real and unexplained. A universe born in a random explosion should have no preferred direction, no axis, no special orientation. And yet the temperature patterns in the oldest light we can detect appear to be subtly aligned with something. Something we have no name for. Something that, if real, would imply that the very early universe had a structure or a preferred direction that we did not put into our model. We are now stacking anomalies. The early universe assembled too quickly. The two methods of measuring the expansion rate disagree. The amount of clumpiness of matter does not match between epochs. Dark energy might be evolving. Dark matter might not be what we think it is. Structures larger than the theoretical limit appear to exist. The oldest light shows alignments that should not be there. Each of these, taken alone, is a single problem. Some of them might dissolve with better data. Some of them might be explained by minor revisions. But the pattern, the fact that so many independent observations are showing tension with the model simultaneously, is harder to dismiss. The standard model of cosmology is not failing in one place. It is showing stress fractures across its entire structure. And we are about to add the deepest fracture of all. The question of whether the laws of physics themselves are constant. There is a number in physics called the fine structure constant. It is denoted by the Greek letter alpha, and it has a value of approximately 1/137. The constant governs the strength of the electromagnetic force, the force responsible for binding electrons to atoms, for holding molecules together, for producing the light that telescopes detect. The fine structure constant is one of the most basic numbers in all of physics. It determines the chemistry of matter. It determines the colors of starlight. It determines the energy levels of atoms and the wavelengths of the light those atoms can absorb or emit. If the fine structure constant had a different value, chemistry would be different. Atoms would be different sizes. Different elements would have different properties. The universe would not look the same, not even close. The constant is supposed to be, well, constant. It should have the same value everywhere in the universe, at every moment in cosmic history, regardless of location or time. That is the assumption that underlies almost all of physics. The laws of nature do not change. They are not parameters that evolve. They are the fundamental rules. In the late 1990s, a team led by John Webb at the University of New South Wales began publishing analyses suggesting that the fine structure constant might not, in fact, be constant. The team examined the absorption spectra of distant quasars, the bright nuclei of galaxies that lie billions of light-years away. As quasar light passes through intervening gas clouds, it gets absorbed at specific wavelengths corresponding to specific atomic transitions. By measuring the precise wavelengths of these absorption lines, you can infer the value of the fine structure constant at the location of the absorbing cloud, which corresponds to a particular epoch in cosmic history. The team's analysis suggested that the fine structure constant might have been slightly different in the early universe. Even more provocatively, the variation might depend on direction. In one direction across the sky, the constant appeared slightly smaller. In the opposite direction, slightly larger. The implication, if the analysis was correct, was not just that the fine structure constant had evolved in time, it was that it varied across space. The laws of physics might be subtly different in different places in the universe. The claim was, predictably, controversial, and it has remained so. Other teams have tried to reproduce it using different telescopes and different quasar samples. The results have been mixed, with most independent analyses finding no statistically significant variation. The community has not converged on whether the original signal is real or whether it is an artifact of how Webb's team processed their data. The disagreement is partially driven by the difficulty of the measurement. To detect a change in the fine structure constant of a few parts per million You have to control for systematic errors at the level of parts per billion. Telescopes are not built to that precision easily. The mainstream position remains that the fine structure constant is constant. But the question has not been definitively closed. James Webb has now been pulled into this debate. The telescope's spectroscopic precision, combined with its ability to observe extremely distant quasars at higher redshifts than any previous instrument, means that for the first time, we have a tool capable of testing the variation of the fine structure constant in the early universe. With unprecedented sensitivity, early results have been suggestive. They have not yet been definitive. The question of whether the fine structure constant is actually constant remains open. And the longer it remains open, the more uncomfortable cosmologists become. Because if the constants vary, the implications are vast. If the laws of physics, as we know them, were different when the universe was 1 billion years old, if the fundamental constants were not constant, then every prediction we have ever made using those constants for the early universe is systematically off, not by a calibration error, by design. The model was built using numbers that may not have applied to the time we are trying to model. The galaxies that assembled on the wrong timescale. The black holes whose mass cannot be accounted for in the time available. The chemistry that arrived earlier than the standard sequence predicted. The structures that appear larger than gravity should have built. All of these anomalies become differently shaped problems if the underlying physics was subtly different in the era when these things happened. Maybe the gravity was stronger. Maybe the electromagnetic force was weaker. Maybe atoms behaved a little differently. Maybe stars produced different elements at different rates. None of these are wild speculations anymore. They are possibilities that the data is forcing physicists to take seriously. There is a philosophical weight to this. The laws of physics, in the way we have always conceived them, are not just descriptions of how things behave. They are the rules of the game. They are what makes a universe a universe. If the rules themselves vary, then we are not living in a universe in the singular sense. We are living in something stranger, a region of larger space in which the rules happen to have certain values, a patch in something we cannot see beyond. Some physicists have argued for years that this is the actual situation. The fine structure constant might be the current value of a slowly varying parameter, like the temperature of a cooling object or the pressure of a settling system. The fact that we observe it to have one particular value might be a function of the moment we happen to live in, rather than a universal truth. The laws of physics as we know them may not be universal laws in the fullest sense. They may be the current values of parameters that evolved. James Webb may, in the next decade, give us enough data to test this directly. The implications either way will be substantial. If the constants are firmly fixed, we will breathe a sigh of relief and continue working on the other problems. If they are not, we will need to rebuild our understanding of physics from much deeper foundations than anyone is currently prepared for. We have one more layer to go, the deepest layer, the one that lies at the very edge of what can be discussed scientifically. We have to talk about what happened before the Big Bang. In the Standard Model, the question is sometimes treated as meaningless. The Big Bang, in this view, was not just the beginning of matter and energy. It was the beginning of space-time itself. There was no before, because there was no time in which a before could happen. Asking what happened before the Big Bang is, in this framing, like asking what is north of the North Pole. The question has no referent. This was a comfortable position for several decades. It allowed cosmologists to set aside metaphysical worries and focus on what they could measure. The history of the universe began at the Big Bang. Whatever came earlier, if anything, was not science. It was philosophy, or religion, or speculation. The position has become less comfortable in the last 20 years, partly because of the cracks in the standard model that we have been describing, partly because of theoretical developments in quantum gravity, and partly because of inflation theory, which itself has unresolved questions that push back against the idea that the Big Bang was a self-contained event. Inflation, again, is the proposed period of exponential expansion that the universe is supposed to have undergone in the first tiny fraction of a second after the Big Bang. Inflation solves several puzzles in cosmology. It explains why the universe appears so uniform on large scales. It explains why space appears so close to geometrically flat. It produces the seeds of structure that eventually grew into galaxies and clusters. Inflation has been a remarkably successful theoretical framework, but inflation has problems. It does not explain what triggered it. It does not explain what ended it. It does not explain whether it was uniform or chaotic. Different versions of inflation theory predict different outcomes for the structure of the universe on the largest scales. Some predict an eternally inflating multiverse, where new universes are constantly being spawned and inflated. Others predict a single inflationary event that ended at a specific moment. We do not currently have the observational tools to distinguish between these scenarios. And here is where James Webb's anomalies start applying pressure to initial conditions. If the early universe was assembling faster than our model says, that might be telling us something about the conditions immediately after inflation ended. If the laws of physics were slightly different in the early universe, that might be telling us about the deep physics of the inflationary phase itself. If there was no inflation, or if there was a different kind of expansion, the entire history of the universe back to the very beginning gets rewritten. There are alternatives to the standard inflationary Big Bang that have, in recent years, moved from the fringes of physics to the edges of the mainstream. The bounce model, in which the universe contracted before it expanded, with the Big Bang being the rebound from a previous collapse. The cyclic universe, in which our cosmos is just one iteration of an endless cycle of expansion and contraction. The quantum tunneling universe, in which our cosmos emerged from a more fundamental quantum state through a tunneling process, like an electron tunneling through a potential barrier. These ideas were once considered exotic. They are now being taken more seriously than at any point in the last 30 years. The reason is simple. James Webb keeps finding things that our model of the beginning struggles to explain. And if the beginning was wrong, if the first chapter is missing or written in the wrong language, then every chapter that follows is built on an incomplete foundation. The early assembly anomalies, the premature black holes, the unexpectedly large structures, the constants that may have varied. All of these might trace back to initial conditions that were not what the standard inflationary picture predicted. There is a haunting aspect to this entire line of inquiry. If something preceded our observable universe, if there was a prior epoch or a parent cosmos or a quantum substrate from which our universe emerged, then most of the evidence of that earlier state has been erased. Inflation, by stretching space exponentially, would have smoothed out almost any imprint of pre-inflationary conditions. Whatever fingerprints existed have been pulled apart so far that they are functionally invisible, but not entirely. The hints we are seeing, the anomalies in the CMB, the subtle structures, the unexpected speed of early assembly, may be the last visible traces of conditions that existed before our visible universe began. We may never be able to read the chapter that came before the Big Bang directly, but the chapter we are reading now, the one James Webb is helping us write, may contain echoes of it. We have followed the strangeness deeper than I think most people expect cosmology to go. We started with galaxies that formed too quickly. We are ending with the possibility that the universe we live in is itself contingent. Not eternal, not unique, not necessary. A particular phase of something larger, with rules that emerged rather than always existing, with a beginning that may not have been the actual beginning, with assumptions we are only now learning to question. The appropriate human response to all of this is difficult to find. We are not built to absorb implications at this scale. We evolved to handle threats that fit in the human field of vision. Predators, storms, cold winters. The cosmological abyss is not designed for human comprehension, and yet here we are, looking down into it, having built the instruments to look. There is a phrase that has been used to describe what this moment feels like for the cosmologists living through it. It is like standing on ground you trusted completely and feeling it move, not collapse, not vanish, just shift slightly, enough to remind you that you do not actually know what you are standing on, enough to remind you that the apparent solidity of the floor was an assumption. The appropriate response to real evidence is not certainty. It is the willingness to stand in the question, to not rush to fill the uncertainty with comfortable answers, to let the strangeness be strange, pulled to maximum scale. An early universe whose assembly we cannot match with our equations, numbers that will not agree with themselves, structures that should not exist, a foundation of uniformity under sustained pressure, constants that may vary across space and time. A beginning we cannot read, and 95% of everything still invisible. What are we actually living inside? That is the question. We do not have the answer. We have a telescope, 1,000,000 miles from Earth, still collecting data. We have a generation of physicists rebuilding their assumptions piece by piece. We have a model that worked for decades and is now failing in ways that we are only just beginning to understand. We have perhaps the most interesting moment in cosmology since Einstein, and the most disorienting one since Galileo turned a telescope on the night sky and discovered that the universe was not what people had assumed. We are not at the end of the story. We are not at the end of this conversation. There is one more act, the reckoning, the part where we ask, what comes next, what survives, what gets rebuilt, and what the data ultimately means for the things human beings actually care about, including the question of whether we are alone. We have spent the last several hours laying out what is wrong with the standard model of cosmology. Now we have to ask what comes next. Replacing a successful scientific framework is not a simple matter. It is not enough to point at the anomalies and say the model is broken. You have to propose an alternative that fits everything the old model fit, plus the new data the old model could not handle. Newton's gravity worked for 250 years. Einstein replaced it with general relativity, not by demolishing Newton, but by producing a framework that included Newton as a limiting case and extended it to handle the situations Newton could not. The replacement was harder than the original. Cosmology is now in the early stages of that kind of replacement process. There is no consensus alternative to lambda cold dark matter. There is, instead, a competition of partial alternatives, each one designed to address some subset of the anomalies, each one with its own problems, each one being tested against new data as the data arrives. Let me walk you through 4 of the leading frameworks. The first is called non-standard inflation. The idea is that the simple version of inflation that has been the textbook explanation for 30 years is wrong, and that a more complex inflationary phase, perhaps involving multiple fields or unusual dynamics, would produce different initial conditions that better match what James Webb is finding. Some versions of non-standard inflation predict more massive structures in the early universe. Some predict different distributions of dark matter. Some predict the kinds of subtle anomalies in the CMB that have been observed. The framework is mathematically rich and produces testable predictions. It is also unconstrained enough that critics worry it can be tuned to fit almost anything. The second framework is called early dark energy. The proposal here is that there was an additional brief phase of dark energy-like behavior in the first few 100,000 years after the Big Bang, before the cosmic microwave background was emitted. This early dark energy would have changed the rate of expansion in the early universe by just enough to shift the value of the Hubble constant inferred from the CMB upward, closer to the local value. It would also have affected the rate at which the first structures could assemble. Early dark energy has emerged as one of the leading proposals for resolving the Hubble tension, and it has the additional virtue of potentially explaining some of the puzzling early galaxy formation observations. Its main problem is that no one knows what would have caused such a phase or why it would have ended when it did. The framework requires the introduction of a new field whose properties are tuned to fit the data, with no underlying theoretical motivation. The third framework involves modifying dark matter itself. The standard picture, called cold dark matter, holds that dark matter consists of slow-moving particles that interact only through gravity. Alternative proposals modify this in various ways. Warm dark matter has particles that move somewhat faster, suppressing the formation of small-scale structure. Self-interacting dark matter allows the particles to scatter off each other through some force we have not yet identified, which would change the way dark matter halos form. Fuzzy dark matter proposes that dark matter consists of extremely light particles whose quantum wavelengths are large enough to affect galactic dynamics directly. Each of these modifications predicts different observational consequences, and each can be tested. The puzzle is that no single modification simultaneously fixes all the problems. Some help with the state tension, some help with the small-scale structure issues. None has emerged as a clear winner. The fourth framework is quintessence and its relatives. We touched on this earlier. The idea is that dark energy is not a fixed cosmological constant, but a dynamical field whose strength can vary over cosmic time. Different versions of quintessence predict different evolution of dark energy. Some predict slow drift, some predict more dramatic changes. The DESI results from 2024 through 2026 provide the first observational support for quintessence over a fixed cosmological constant, and the support has been strengthening with successive data releases. Quintessence does not, by itself, solve all the problems, but it has the advantage of being directly testable, and the evidence has been moving in its favor. None of these frameworks resolves all of James Webb's anomalies simultaneously. This is not a failure. It is what we should expect. The replacement for a major scientific framework does not arrive fully formed. It arrives through competition, through testing, through the slow accumulation of data against which each framework either survives or fails. Some of the four frameworks I just described may end up being part of the final picture. Some may be discarded, some may be combined. The framework that eventually replaces lambda CDM, if any single one does, will probably look different from any of them. There is a historical pattern worth recalling here. Newton's physics ruled for 2.5 centuries. It worked spectacularly well for the situations it was built to handle. It predicted the orbits of planets to great accuracy. It predicted the return of Halley's Comet. It predicted the existence of Neptune, found because Newton's gravity required it to explain the orbit of Uranus. But Newton's physics also had problems. The orbit of Mercury did not quite match what Newton predicted. There was an anomalous precession, a slow drift in the orientation of Mercury's elliptical path that did not fit. For decades, astronomers tried to explain it. They proposed an undiscovered planet inside Mercury's orbit. They proposed an oblateness in the shape of our home star itself. They proposed various tweaks to the math. Nothing worked. Einstein's general relativity in 1915 predicted Mercury's precession from first principles. The match was exact. The framework that replaced Newton's was not built by patching Newton. It was built by stepping back and asking what space and time actually were, and arriving at a more fundamental picture in which Newton's results emerged as approximations valid for weak gravity and slow motion. The replacement framework was deeper than the old one. It included the old one as a special case, and it predicted things that Newton's framework had no way to predict. The same pattern happened with quantum mechanics. Classical physics could not explain why atoms did not collapse, why heated objects emitted light with a specific spectrum, why electrons sometimes behaved like particles and sometimes like waves. Each of these was a small anomaly. Together, they pointed toward a deeper framework in which classical physics emerged as the macroscopic limit of something stranger underneath. Each replacement, when it came, was harder to understand than the framework it replaced. Einstein's curved spacetime is harder to picture than Newton's flat space. Quantum mechanics is harder to grasp than classical mechanics. Each answer opened a deeper door. James Webb has opened a door. What lies behind it is, at this moment, a collection of competing theories, unresolved tensions, and data that does not yet fit cleanly into any single framework. That is not a comfortable place to be. It is an honest one. We are in the middle of a transition. The next framework is being built right now in conferences and papers and arguments between physicists. We will probably not know what it looks like for another decade, but the seeds of it are in the data we have been discussing. There is one more piece of James Webb's contribution to all of this. A piece that connects the abstract cosmological questions to something closer to the human heart. James Webb is not just a telescope for studying the early universe. It is also a telescope for studying exoplanets. Its infrared spectroscopy is sensitive enough to detect the chemical fingerprints of atmospheres around planets orbiting other stars, planets that no previous instrument could examine in such detail. And one of the explicit goals of James Webb has been to look for signs of life. The most famous attempt came in April of 2025, when a team led by Niku Madhusudan at the University of Cambridge announced what they described as the strongest evidence yet for a possible biosignature in an exoplanet atmosphere. The planet was called K2-18b. It orbits a red dwarf star, 124 light-years from Earth, in the habitable zone of its star. The planet is what astronomers call a sub-Neptune, with about 8 times Earth's mass and about 2.5 times Earth's radius. The team had been monitoring its atmosphere for years. The new analysis claimed the detection of dimethyl sulfide and dimethyl disulfide, 2 molecules that, on Earth, are produced almost exclusively by living organisms. Dimethyl sulfide is what gives the ocean its distinctive smell. It is produced by phytoplankton. Dimethyl disulfide is similarly biological in origin. If these molecules were really present in the atmosphere of K2-18b in the quantities the team reported, The most natural explanation, by a wide margin, would be biological activity. The announcement made headlines around the world. Scientists were rightly cautious about overinterpreting it. Madhusudan himself emphasized that the detection was at 3 sigma significance, well below the 5 sigma threshold normally required for a scientific claim of this magnitude. Then, the reanalyses came, and the picture got considerably less clean. In July of 2025, a NASA-led team published an independent analysis of the same data and found no statistically significant evidence for dimethyl sulfide. The team confirmed that K2-18b had a water-rich atmosphere with methane and carbon dioxide, but the biosignature signal that had made headlines was, in their analysis, indistinguishable from instrumental noise. In August, another team led by Kevin Stevenson at the Johns Hopkins Applied Physics Laboratory reached a similar conclusion. They found that the mid-infrared transit spectrum, where the dimethyl sulfide signal had been identified, was highly susceptible to unresolved instrumental systematics. Different choices in how the data was processed led to radically different conclusions about the atmosphere. The signal of life in their analysis was best understood as red noise rather than a real detection. A separate study, published in the journal Astronomy and Astrophysics in August of 2025, looked at the K2-18b observations across multiple JWST instruments and arrived at the same conclusion. The original signal could not be reproduced through independent analysis. Other molecules, particularly ethane, could explain the same spectral features without requiring any biological involvement. The team concluded that there was, at present, no statistically significant evidence for biosignatures in the atmosphere of K2-18b. This is what science looks like when it works correctly. A claim is made, the data is released. Independent teams analyze it, they reach different conclusions, they publish, the debate continues. Nothing is settled until multiple independent analyses converge on the same answer. K2-18b is not at this moment evidence of life beyond Earth. The original team has not retracted its claim. The skeptical teams have not declared the question closed. The current state of the science is genuine uncertainty, leaning towards skepticism. Whatever is in that planet's atmosphere, the data is not yet good enough to tell us with confidence. But the larger question that K2-18b raised, the question of whether life might exist elsewhere in the universe, is now more central than it has been in a long time. And James Webb's discoveries in cosmology have changed the shape of that question. Here is the connection. If the universe builds structure faster than we assumed, if galaxies assembled in less time, if heavy elements were produced earlier, if stellar generations cycled more rapidly, then everything downstream from those processes happened earlier too. Planets formed earlier. Chemistry got more time to develop. Liquid water environments existed for longer in cosmic history. The window for life to emerge and evolve, if life is something that can emerge from non-living chemistry given the right conditions, was larger than we previously calculated. That sounds, at first, like good news. More galaxies, more planets, more chemistry, more time. Surely that means more life, but it makes the silence harder to explain. The Fermi paradox is the famous puzzle, named for the physicist Enrico Fermi, who allegedly posed it during a lunch conversation at Los Alamos. Where is everybody? If the universe is so vast and so old, and if life can arise on planets in habitable zones around stable stars, why have we not detected any clear evidence of intelligent life beyond Earth? Why is the sky not full of radio signals? Why are there no obvious technological signatures? Why does the universe appear on every measurement we can make to be empty of anyone but us? The Fermi paradox has many proposed solutions. Maybe life is genuinely rare. Maybe intelligent life is rarer still. Maybe civilizations destroy themselves before they can become detectable. Maybe they exist but communicate in ways we cannot perceive. Maybe they are deliberately silent. Maybe the universe is simply too large and the time intervals too vast for any two civilizations to easily overlap. James Webb's discoveries make the paradox harder, not easier. If the universe has been building structure, planets, and chemistry for longer and more efficiently than we thought, then the time available for life to emerge and spread has been longer than we calculated. The universe is older, in functional terms, than it appeared. More opportunities, more cycles, more attempts at biology. And yet, here we sit, on our small blue planet, with our radio telescopes, listening to silence. Either we are missing the signals, or life is rare. Or something happens to intelligent civilizations that we are not yet seeing. If life is common, we are one instance of a process the universe has been running for billions of years in billions of locations. If life is rare, then we are a single point of awareness inside a universe stranger than we imagined, the only place where the universe has begun to look at itself. Either possibility is staggering in its implications. Either possibility deserves serious thought. James Webb will not resolve this question. The telescope can detect biosignatures with great difficulty on a handful of nearby exoplanets. It cannot survey enough of the sky to give us anything close to statistics. The Nancy Grace Roman Space Telescope, scheduled to launch later this year, will help. So will the next generation of ground-based, extremely large telescopes. So will future missions designed specifically to image Earth-like worlds around Sun-like stars. The data is coming, slowly, decade by decade. What James Webb has done is move the question from philosophy to measurement. We are no longer guessing about exoplanet atmospheres. We are observing them. We are no longer estimating from theory how quickly the universe built itself. We are watching it happen in the light from 12 billion years ago. The questions that used to belong to bar conversations and science fiction are now in the daily routine of observational astronomy. We are going to spend the next century answering questions that, when this telescope launched, were still being asked in their abstract form. Some of the answers will be reassuring, some will not. All of them will reshape what it means to be a human being looking at the night sky. There is a particular image we have come back to several times in this story, and it deserves one final return. It is the image of a grain of sand held at arm's length. The original James Webb Deep Field, the photograph released to the world in July of 2022, captured a patch of sky no larger than that. In it, the telescope found a vast number of galaxies, each one containing hundreds of billions of stars, each one with its own history, its own structure, its own chemistry, its own past and future. The image was meant to provoke wonder. It did. But over the following 3 years, that same image became something else. It became a kind of guide to the strangeness we have just spent the last 2 hours exploring. The galaxies in that tiny patch were not what they were supposed to be. Some of them were too mature for their age. Some of them had black holes that should not have been there. Some of them showed structures that did not fit the model. The patch was full of anomalies. The continent, the astronomer described, was an unfamiliar continent. There are at least 4 meanings in this. 4 ways of holding what James Webb has shown us. The first meaning is that science is working correctly. The model was wrong, and the data revealed it. The system designed to discover the truth about the universe is functioning exactly as it should. Anomalies are not failures. They are evidence. They are how knowledge moves forward. The second meaning is that the universe owes us no simplicity. The Standard Model worked for 30 years not because the universe was obligated to be that simple, but because we had not yet looked closely enough to see the complications. Now, we have looked more closely. The complications are emerging. We should not be surprised. We should not be disappointed. The universe was always going to be at least as complicated as we are capable of measuring, and probably more. The third meaning is that we are inside a rare moment. Periods of genuine paradigm shift in fundamental physics happen a handful of times per century. The shift from Newtonian gravity to general relativity. The development of quantum mechanics. The discovery of the expansion of the universe. The discovery of dark energy. We are alive during one of these moments. The next textbook of cosmology, the one our children will study, is being written right now, in real time, by people who are still figuring out what to write. The fourth meaning is the largest, and perhaps the most important. The universe has never, not once in the history of science, turned out to be smaller than we thought. Every answer has made it larger. The Earth, once the center of the cosmos, is a small planet orbiting a small star. That small star, once unique, is one of hundreds of billions in our galaxy. That galaxy, once the entire universe, is one of trillions. The cosmic microwave background, once the edge of what could be seen, hides further structure behind it. The known particles, once everything, account for 5% of what exists. The visible universe, once everything, may be just one region of something vaster. Every time we have measured more carefully, the universe has grown. It has grown in size, it has grown in age, it has grown in complexity, it has grown in the number of questions it can pose. There is no reason to expect this pattern to reverse. The model we built was not big enough. It worked beautifully, within the range of conditions we had access to. When James Webb extended that range, the model began to creak. That is what models do, at their boundaries. They creak first, they fail later. Then they get replaced by something larger. The something larger is being built now. We cannot fully see it yet. We can see fragments of it. Early dark energy, modified inflation, evolving dark energy. New ways of thinking about dark matter. New ways of asking whether the laws of physics themselves are stable. Quintessence and bounces and cycles and tunneling. The fragments do not yet add up to a single coherent picture. But they will, probably not soon. But eventually, in the meantime, we live with the strangeness. The galaxies that should not exist, exist. The numbers that should agree, do not agree. The constants that should be constant, might not be constant. The beginning we thought we understood may be more complicated than we thought. Or maybe only one of many beginnings, or maybe something we have not yet learned to name. A telescope 1,000,000 miles from Earth is still out there, collecting light, ancient light, from the edge of what we can see. Its mirror is still oriented away from the sun, in permanent darkness, free of the radiation that would interfere with its observations. Its instruments are still cold, cooled to within a few degrees of absolute zero, sensitive to the faintest infrared signals from the deepest cosmic distances. It is still working. It is still finding things. Some of what it is finding will eventually be understood. Some of it will turn out to be measurement artifacts. Some of it will turn out to be statistical flukes. Some of it will turn out to be exactly what it appears to be, evidence that our universe is more complicated, more interesting, and more strange than the comfortable framework we built to describe it. We do not know which discoveries will fall into which category. We will only know in retrospect, decades from now, when the next framework has settled and the current confusion has become clear. What we do know is that the question has been asked in a way that cannot be unasked. We have built an instrument capable of looking further than any before it, and what it has shown us is that we did not understand what we were looking at. We were sure we did. We had reasons to be sure. The reasons were good. The certainty was earned. And then the certainty turned out to be premature. This is the moment. This is the place where cosmology stands. Not in collapse, not in defeat, in the early stages of a reckoning, with more questions than it had 3 years ago, with more humility than it had a decade ago, with more data than ever before, and less confidence about what the data means. And in that light, the ancient light from the first galaxies, the universe is still speaking. We are only now learning how to listen.